Okay, I hope you can see the presentation. So let's start. So good morning to everybody. I'm Flavio Pignone, a researcher at the SIMA Foundation, and in this presentation I will show you what has been done in the recent years in the development of rainfall data product and consequently on improving hydrological modeling. The idea that moved all this work is that the multi-sensor data fusion proved that combining data from rain gauges and remote retrievals represents the best way to obtain an enhanced and more reliable evaluation of a quantitative precipitation estimation that improve hydrological modeling for river discharge estimation. The information provided by the remote sensor may be used to condition the information from rain gauges, which is limited in the terms of spatial representativeness. In this way, an estimate of the rainfall field containing a more realistic spatial structure constrained to the rain gauge data can be produced. The presentation will describe the theoretical background and some examples for merging with radar and satellite data, and how to improve the discharge modeling. A modified conditional merging approach developed from the original conditional merging proposed by Sinclair and Pegram will be illustrated. So, the Italian coastal city, as many other in the Mediterranean, have been affected by several floods and flash floods in the past. The typical scenario is a city built between the sea and the mountains, whereby the basin morphology are characterized by numerous small and steep river catchments, sometimes with the final part passing through a covered riverbed. So a typical event is usually a convective process that has its origin in the warm Mediterranean Sea and subsequent orographic lifting produce heavy rainfall. There are many examples where the rainfall accumulated in 1 hour from one of these events accounts for the entire monthly average for a particular location, and the rainfall accumulated in 1 day can sometimes account for the annual average. In some particular mesoscale and small-scale conditions, the events could be stationary, bringing the worst result in small and steep basins. These rainfall events can have dire consequences for the local population. So this leads that the capability of correction of observation of this correct observation of this phenomena along with public education can significantly reduce the loss of human life and damage to property. One of the major challenges is that the mountainous nature of the region creates many problems for radar observation and the rain gauge network, in spite of its high density, does not allow for good spatial estimation in real time. These two pictures show the case of Genoa flood, one in 1970 and one in 2011. In this case, the amount of rainfall was more than 500 millimeters in 6 hours. This produced dramatic hydrological consequences, with many creeks overflowing and their banks accompanied by a large number of mud floods and landslides. To prevent or face this problem, a good knowledge of the domain and the behavior of a hydrological cycle is fundamental. The ability of estimation of spatial and temporal distribution of rainfall events, their correct spatial location, and the reliable estimation of the volume of water fallen are essential information for hydrometeorological application, especially related to civil protection action. Current technology provides a number of instruments such as weather radar, satellite sensor, that as the most traditional rain gauge allows the observation of precipitation. Depending on the availability of all the data provided from different data sources, an innovative idea is to combine the different observations in order to obtain an estimation of the optimum range of precipitation. These methodologies, called data fusion or merging, were studied since 1980, but there weren't the wide range of sensors that we dispose now. Since the 2000, with the incremental measuring ability and the data computing, merging rainfall from multi-sensor took a new interest. This approach is the most promising research direction for the estimation of precipitation fields, even at higher resolution. The idea is to use is to use methods that infer the reliability quantitative through punctual observation of precipitation obtained from a rain gauge network with the ability of observation from remote radar or satellites data to provide a detailed description of the spatial structure of the rainfall field. Merged field can be used in both real time for purposes of civil protection, both in different areas of research from hydrology to forest fire prevention. Every of these type of observation has different advantage and disadvantage. For example, rain gauges are the traditional tools for precipitation measurement and measurement. They are fairly cheap, easy to maintain, and provide a direct and accurate measure of precipitation in the point of application. They offer measurement with high spatial resolution, but with very little information about its spatial distribution. The weather radar instead give a good description of the spatial and temporal pattern of precipitation over a large area, but are affected by uncertainties in the estimates of precipitation due to the indirect nature of the same. The measurement of precipitation is in fact obtained through empirical relationship by measuring the reflectivity or other measured variables. The estimation of precipitation from weather radar, in addition to being dependent on the conversion of reflective rainfall intensity, can be affected by problems such, for example, the partial or complete obstruction of the beam observational. Moreover, satellites guarantee an optimal spatial coverage, even better than that of the radar, but also estimate the precipitation in an indirect manner. Mainly, satellites are divided into geostationary and low Earth orbit. Satellite observations are affected by estimation errors with varying degrees of reliability or shell space-time in relation to the type of satellite and sensor used. Let's see now. Here is illustrated a typical probabilistic hydrological chain based on observation. As you can see, the idea is starting from different kind of data to produce a better rainfall field that should be used in different ways, from nowcasting to hydraulic model passing through the hydrological modeling. So the focal point is the knowledge of a rainfall field that guarantees reliability. In the next slide, I will describe what I have done since my degree on these topics. In the fall 2011, I started from what is available in terms of observation. So the data that were and are now available are the rain gauge network. The rain gauge network is composed of stations in telemetry that records continuous measurement of rainfall accumulation and transmit them in real time. Nowadays, there are more than 4,000 stations, and the largest portion of them is the tipping bucket type. The mean density of the network is 1/100 square kilometers, with the highest of 1/50 kilometers here in the Liguria region. The temporal resolution now is approximately at 5 minutes. Other sensors are the weather radar. They are devices that provide the estimation of rainfall in time and space in real time with good accuracy and temporal availability. The spatial resolution is 1 kilometer. Of the Italian radar network is 1 kilometer and covers the whole territory. Some portion of the domain are covered by more than one radar, so it's possible to take the better data related to the quality of the different measures. The temporal resolution is now 5 minutes. It's written 10, but now is 5 minutes. And finally, there are also the satellite data products, but this product came later in my study. At the time, we were involved in the HSAF consortium marginally, so the usage was more for researching purposes. The method I'm going to explain was born to merge rain gauges and radar, but it's later also applied also for the HSAF product, satellite product, and many applications were done in the last year. So let's start. First of all, knowing what data are available forced the choice of methods to be applied. After a literature overview, I found a lot of methods, very different one from each other. Here you can see a short list. Every of these methods has a totally different approach. So, for example, the geostatistical methods are based on the evaluation of the spatial correlation of the data, trying to see if observation of neighborhood points have less variability compared to the observation made between distant points. The objective is, therefore, to evaluate the effect of the position of the measuring point on the variability of the observed data. Such variability is usually modeled by semi-variogram, a mathematical function which assesses the variation of degree of correlation of points at increasing distances. Instead, the adjustment are historical methods of adjust that were applied in the data fusion of ground instruments and the radar rainfall. Through the calculation of an adjustment factor derived from the differences of the two datasets, a recalibration of the field is applied that minimizes the difference between the observation and the rainfall radar observation. There is no real merging of the data, but only a bias correction and the recalibration of the source of the data with respect to another. Instead, there are also Bayesian models. Bayesian methods are based on the application of statistical theories which help to identify the more realistic value of the field based on the data characteristic. In case of rainfall, this methodology gives in output the probability to have a certain amount of precipitation conditioned to having a particular set of observations rather than range and satellite. The Bayesian methods do have the characteristic of being direct and intuitive and are well suited to the problem decision making. What makes the decision difficult is the uncertainty related to the lack of knowledge of some relevant facts of parameters. The multiscale ones instead. The multiscale methods explore the statistical properties at different spatial or temporal precipitation fields. In recent years, models have been developed on the stochastic space-time characteristic of precipitation, in which are inserted theories of the multiscale representation of process. The multiscale methods can be beneficial as they ensure both the elimination of both background noise and the possibility of building fields in spatial scale and going to extract information from the coarser spatial scale. Finally, there are also the neural network method. Recent research has shown how the technique based on the neural network can be used with success for the estimation of the precipitation fields from multi-sensors. The neural network is a non-parametric method used for the representation of the functional relationship between the rainfall estimates derived from different measured sensors. The advantage of neural network is that the relationship between the sensor is derived from the training dataset and is not influenced by the characteristics of the sensor themselves. Furthermore, neural networks are effective and easily improved if you have available datasets that are representative and reliable that take into account new information, such as, for example, seasonality. So a good method based on a neural network must be able to adapt to new input while maintaining reliability and the computational speed. The methods based on a neural network have the advantage that given a sufficient quantity and the representativeness of the dataset as input, to adapt to change resulting from additions of data or variation of the same, in addition to providing the results where there are no accurate analytical models, even in the presence of background. Just to conclude, in conclusion, despite the availability of various methods, it was not clear which approach was the best or if there is one unique way to estimate the optimal rainfall precipitation field. A comparative analysis of the various methods of merging has never been done, so the advantage and the disadvantage of the different algorithms are not yet explored. So the availability and the quality of the data, that the need of stable and quick results suitable for operational civil protection case lead to choice of just geostatistical method. So in the next slide, I will show you the method based on the geostatistic. But what is the geostatistic? In the geostatistic, the idea is to verify if and how observation close to another is similar while observation far from other present bigger variability. The goal is evaluate the observation variability due to the position of gauge within a network and use this information for build the interpolated field. The origin of geostatistics was in the past century when Danny Kriege began research on using statistics to find and evaluating mining, applying statistical research methods to already established data that was gathered from the drilling to find potential new mining sites. In 1951, Kriege became famous in the research world when he formed the basis for a special interpolation technique that would later be known as kriging. So here I'm going to present a new method based on the kriging paradigm that is called GRISO, Geostatistic Rainfall Interpolator of Scattered Observation. The idea is to use a new method instead known one due to the fact that there are a couple of interesting advantages that are used later on. The GRISO method, like the most known kriging technique, assigns weights according to a data-driven weighting function and the implementation of producer fields that passes exactly through all known points in the estimation. In this work, there are two needs: passing to describe quantitatively how variable varies spatially, and to predict its values at places where we have not sampled. The GRISO interpolated field presents two main constraints: passing through the observation. It means that on the gauge location, the output field maintains the value measured, and tendency to a fixed value. The interpolated field far from the gauge location and their influence assume a specific imposed value. To obtain the aforementioned characteristic, it is necessary to define or estimate a couple of parameters: the covariance kernel function, the shape of this cone, and the correlation length, so the range of influence. And here I'm going to describe the linear equation system, so how to solve the GRISO interpolator. The interpolation algorithm GRISO is a mathematical procedure that allows to generate a continuous field F from the observed values V. It is based on the use of variogram during the evaluation of the mutual correlation between points, then on the solution of the linear equation system derived from. Here is described the linear equation system, which is able to solve the interpolation problem. GRISO and kriging algorithms are very similar, so the equations that describe the influence of one gauge on the neighboring ones are the same. The only difference is in the linear equation system in the last equation. Kriging, in fact, imposed the sum of weights equal to 1, while GRISO imposed that the weights are scaled for obtaining a tendency value. So, as said before, to obtain the aforementioned characteristic, it is necessary to define or estimate a couple of parameters that are the covariance kernel function and the correlation length. The covariance kernel K here is the mathematical formulation representative of the semi-variogram that defines the weight coefficient K related to the influence of the S point of measurement. In other words, the means no correlation, and 0 means not correlation, and 1 corresponds to the maximum correlation. The correlation here is maximum in the range gauge location, and drop to 0 after the length of the correlation length. Here, in the last equation, the mu k are the areal mean of single range depending on the kernel used. So is the area of this function. Depending on the kernel covariance and length of correlation adopted is evaluated the areal mean of the single range. Here, the V are the range observation of the N gauges, and here is used directly the range observation, while this value, the value is the tendency value that is defined is defined a tendency value of the rainfall field. This value is the one that is reached far from the gauge and their influence. Okay. The GRISO method now was developed to work in two different modes. The modes are a priori, so that means that imposing a kernel covariance function and the correlation length a priori, or in the estimation way, estimating kernel covariance function and correlation length for every single point of measurement. On one end, using the a priori mode is difficult to well represent the real pattern of the rainfall. On the other hand, the estimation mode requires a long computational time, especially in case of high density network observation. So the idea is to build this linear equation system and then solve this equation and evaluating the weight W. The interpolated rainfall field F is obtained simply summing the product of covariance kernel used with the weight W of every rain gauge and rescaling with the tendency value according to the formula here described. So let's see now some examples. As said, this method of interpolation was developed many years ago and now is used operationally at the CIMA Foundation. For example, on the WebGIS platform developed by CIMA, called the WETRA, there is a specific layer of rain gauges. Here, just another view of the layer. So every rain gauge has the continuous series of data for single rain gauges. So from this data, it is possible to apply the GRISO method and obtain the interpolated field, rainfall field. The idea now laid behind this map is to use the a priori mode to obtain the map in just a few seconds. So here is just an example. Okay, no, there are no other examples. Now, after the method description, there is also the validation of the GRISO method. In particular, to conduct the validation was followed this 7 step. So first of all, identification of a large number of events, identification of different spatial density, use the radar map as a benchmark to try to reproduce the field with the GRISO interpolator, sampling the radar input with the new density specified, and then produce the map of interpolated using GRISO and using kriging. Then apply different statistical score to assess which is the better method. So as said, identification of a large number of events, identification of different spatial density are choose this value, are just value. Here, as said, we use the radar map just as a benchmark. No information from radar map are used now. Here, just a zoom. Sampling the radar input map with the density specified before, and use GRISO and kriging to obtain the interpolated rainfall field. So the idea is produce a lot of replicas with the different sampling density. Here's some example, and apply the different statistical score on the new fields, just to understand which is the better mode. Here some result. Some scores show how GRISO gives slightly better result, but in general there is no big difference between GRISO and kriging, and this is expected due to the fact that geostatistical method and the linear system equation is similar. But according to the previous result, GRISO and kriging have generally similar statistical score, but the GRISO method have a few advantages respect to kriging that are not negligible. reducing the computational time for operational purposes, possibility of using different covariance structure for spatialization of rainfall, possibility of using a covariance structure that is based on high resolution. A center of shower should be located between rain gauges and not necessarily on one of it. This is important. In particular, this is very important because usually the maximum of rainfall is located on the position of rain gauges, but in this with this method should be also located in any points between the rain gauges. Probably you can see this point, this green point that are the rain gauges, and the center of shower is between them. So now, until now, I showed you the rain gauge interpolator. This method is the one used within the conditional merging application. Within the geostatistical category, the work of Sinclair and Pegram that have proposed the conditional merging in 2005, a merging algorithm which extracts the information content from the observed data and use it within an interpolation method to obtain the rainfall maps was identified. The rain gauges provide the punctual measure of the observed real rainfall, while the remote sensor supply rainfall estimation maps, which give an idea of the correlation and structure of the covariance of the observed field. This is the steps to reproduce the conditional merging as Sinclair and Pegram stated. So first of all, start with the rain gauge observation, then the remote observation on the same spatial and temporal domain. As I said before, due to the time when the algorithm was developed, the work was conducted on the radar data framework, then was transferred also to the satellite data. So the third step is interpolate the data from rain gauge. The fourth, sampling the remote data at the ranged location and interpolate them. Make a difference between step 2 and 4, so between the remote observation and generation of the interpolated data. And finally, sum the last map of differences to the rain gauge interpolation to obtain the emerging rainfall field. And this is a result. Now, this is as I told you, the method of Sinclair and Pegram. But during my degree and PhD, I developed some innovation that I describe now. So the first of all is the preprocessor of rain gauge data. This is not a real innovation, but a necessary work to be done, because according to WMO guide, the amount of precipitation measured in the gauge is less than the actual precipitation reaching the ground due to different causes. It should be decided if correct the measure according to specific equation or rely on the measure themselves. In my case, I prefer to use the observation as they are with no modification. Moreover, a temporal and spatial filter are adopted. In fact, due to the fact that the final merged field used as ground truth the rain gauges, every error in the input are transferred to the output. So to avoid some evident error that should generate a spike in the map, I feel the filters are applied. If you're interested in more detail, I can give you maybe later. But the idea is to compare every measure in space and time and reject the measure if not under defined thresholds. To give you an idea, the rejection rate is less than 0.05%, so there is no significant reduction in the quantity of data. The real innovation is the usage of GRISO method as described before, in particular the ability of evaluate the local correlation. Probably there was an animation on this slide, so you can see it properly. Let me see if I can do something. No? Okay. The other innovation is the correlation. The other is the way to evaluate the correlation. The correlation is not evaluated on the rain gauge, but from other sensors. as in this case is from the radar one. In fact, the covariance structure estimation for every rain gauge is derived directly from the remote sensor rainfall field. To have a good estimation of the correlation, it is necessary to have enough information of all the legs involved. The legs are discrete distance, so more are considered, more value of correlation are known. Then it is possible to recognize a spatial pattern. The modified conditional merging using the pixel radar map information is able to evaluate the correlation between the leg equal to the spatial resolution and the leg identified as the maximum distance in which rain gauge have influence. The result is a continuous series of data where it is easily to fit a kernel function. Unfortunately, I can't show very well, but the other innovation is a consequence of the first and regard the possibility of fitting the empirical correlation of 3D covariance kernel note in literature. This operation, in truth, creates lots of information because fitting an isotropic kernel implies making a mean of the structure. The unique reason to apply this step is due to the fact that leads to a stable and feasible linear equation used to interpolate. Again, some problem of the figure, but what I can show you is that just an example of the correlation, evaluation of the correlation. In fact, as you can see, depending on the rain gauge, it's possible to have a different estimation of correlation and length. Here in the black line is the empirical correlation, where it is possible to fit the different shape of the covariance kernel to find the best one. In the figure, the blue lines are the different rain gauge correlation estimated for different rain gauge. The red line is the mean of correlation, and the green line is an hypothetical a priori correlation. So what I want to show you, that using this method, you can estimate the local covariance kernel that better represent the real rainfall precipitation field. Instead, use a mean of correlation or a priori correlation. And here some example of application. This is again for the famous Genoa floods on 4 November 2011. Other examples for the whole Italian domain. Now, again, also in this case, I can load and navigate the different layer on the water platform. So here an example, the the rainfall field, the radar, in this case, the radar observation. I choose voluntarily this map to demonstrate a thing. In the figure, you can see a strange rainfall field here, with the yellow and green circle. These are due probably to the melting layer error. So when the radar beam passes through the layer of zero thermal, the signal reflected suggests to the radar that it's raining, but probably is not. The merging method, the final product has inside what was observed by the radar as correlation, but using as ground truth the rain gauges, the field is corrected and it seems more realistic. Moreover, last comment I have to do is here, sorry, here regarding the boundaries. In fact, in this case, is outside the boundaries as national boundaries or the sea, there is no rain gauges, so the information it's only provided from the remote sensor. So in this case, from the radar observation. This behavior creates some discrepancies in the layers, but there is no influence for the consequent hydrological model. So here also for the merging method, a validation was done. The general framework is the same used for GRISO, so following all the steps that are identification of large number of events, identification of spatial density, application of the modified conditional modified conditional merging with using the GRISO method or the kriging one, application of different statistical score, and here are some score, but more interesting this one. In this case, especially the PDF, the ensemble of PDF differences is very interesting because as you can see, the blue one is corresponding to the modified conditional merging with the GRISO interpolator method, respect to the kriging one. So the new method proposed is showed a more peaked and narrow PDF that demonstrates that is a better method with the innovation that I explained, respect the original conditional merging. And the last comment I wanna make is regard the power spectra of the different maps. The red line here is the power spectra of the radar one, while the blue line is the power spectra for the interpolated field with GRISO. As you can see, the black line is the merging one and is following the radar one. So that demonstrates that the final product follows the correlation structure provided by the remote sensor. That is not possible, and so this is the main interesting thing to show on the slide. Here are other examples, but probably it's too late to see everything. And now, finally, as I said, the method was developed for the radar framework, but was also developed for the HSAF precipitation product. And here are some examples. So just to recap the method, they started from a range observation. Then the range is interpolated with the GRISO method, with the correlation estimated from, in this case, from satellite product, that in this case is the H5D. And again, the rainfall map, the satellite product is sampled on the rain gauge location, interpolated in the same way with the GRISO method, and here the difference, and finally is obtained and merged the field that passed through the rain gauge observation with the correlation of the satellite observation. Here are some quick example. In this case, rain gauges, rain gauges, radar, and satellite product, and here merging with the radar and merging with satellite. Here a scatter plot between radar and satellite product. As you can see, are let me say more similar the results, because as you remember, on the land, the main measure, the important measure, the ground truth derived by the rain gauges. So let's see other example. These are not so interesting. Where is this one is interesting because, again, rain gauges, radar, and satellite, as you can see, are different, the observation, while in the merging final map with the radar and with satellite, on the land, the behavior of the rainfall field is similar. On the sea is totally different. And this is reflected here in the scatter plot, because in this case, the scatter plot is essentially a comparison between radar and the satellite, because on the sea there is no range observation. And the other example, to conclude, because maybe it's late. So in this work was presented a new data fusion technique for multi-sensor quantitative estimation of precipitation. This method is based on the geostatistic and is called Modified Conditional Merging. The algorithm is described directly from the conditional merging proposed by Sinclair and Pegram. The difference are the innovation added to the original methodology in order to improve the quality of the merging product, also in relation to the characteristic of the data set used as input. The main innovation is the estimation of the local correlation for every linkage. In consequence, the merged map can pass through the value measured at the surface with the correlation observed by the remote sensor. Moreover, another innovation is the new method to interpolate the linkage observation called GRISO. This algorithm is a different application of the geostatistic method known as GRISO. So, the knowledge of the rainfall field plays a crucial role in the prediction based on observation. As my colleague will show you later, an improvement of the input is reflected on an improvement of the hydrological model. So, I conclude my part. I leave the floor to Simone Gabellani.
Thank you, Flavio. Thank you for this presentation of the method and the combined use of satellite and ground data. So I'm Simone Gabellani, a colleague from CIMA Foundation of Flavio, and I will show you the application of the satellite precipitation product, in Sibiri H03B and the HAC Sibiri H05B in a distributed hydrological model, and I will show you the use of the satellite data set directly as input to the model or through the merging between satellite and ground data with the technique that Flavio illustrated us. In the HSAF framework, we yearly perform an hydro validation of all the HSAF products. Probably you have been introduced during the previous session to these topics. Essentially, the hydro validation is the test of the HSAF products, all of them, soil moisture, precipitation, and snow, using this product in a hydrological model. So directly, if it's possible, as input, or through the data simulation. For example, soil moisture is not usually used directly in hydrological modeling, but is simulated. In the case of precipitation, we can use directly the data set as input. Okay. The products that we used, that we usually test in the hydro validation are H03B and H05B. They have been already introduced in the previous session. The first one, 03, has a stem frequency of 50 minutes, while the H05B is accumulated precipitation on different time steps. So we used those products as input for a distributed hydrological model that we developed named Continuum. It's a complete and distributed model. So the fact that the model is fairly distributed it's important because it can benefit from the it can benefit from a distributed observation of the precipitation fields. It completely solved the mass balance and the energy balance equation and reproduced the spatial and temporal evolution not only of stream flow and discharge, but also of evapotranspiration, soil moisture, snow water equivalent. And it's freely available. You can find it on the GitHub platform. Just some example to show you the output of the model. We use the model operatively for the Italian civil protection for flood forecast in different section of the Italian river network. In each point of the river, the model gives you the discharge time series, both in observation mode or in forecast. So when the model is coupled with the meteorological forecast, it gives you the forecast of discharge. But due to the fact that it is distributed, it can also reproduce the evolution of the soil moisture. We implemented the model in Italy with a spatial resolution of 500 meters and the hourly resolution of 1 hour. In this picture here, you can see the soil moisture map for a specific day with a 500-meter resolution, and these other pictures illustrate the magnitude of event represented as reaching period, so the severity of the events in each point of the river network. This slide just illustrates the characteristic of the model. For the HSAF hydrovalidation, so in the framework of the HSAF project, we have 7 test basins that are here in the north part of Italy. They range from about 1,000 square kilometers, so a medium-sized basin, to less than 100 square kilometers, so quite small basin here, pink at this part. First of all, and we perform the hydrovalidation yearly, so from each year, considering the period from June to May of the next year. I reported here the comparison between the average catchment values of precipitation for the product H03B for one of the test basins. In green, you can see the precipitation from rain gauges interpolated using the GRISO meter that Flavio showed us. And in red, you can see the satellite precipitation average and basin scale. So if we consider hourly data, so the correlation is quite low. The correlation is bigger if we consider daily accumulated values. But the classical things that we usually see every year is an underestimation of the precipitation. So satellite usually underestimates the precipitation. And this is the comparison between ground data and satellite, again, red on a monthly basis, also in this case. So in every month, usually you have an underestimation. This is another year, 2012, 2013. The behavior is very similar to the previous period. And the two products that we usually analyze, so 03 and 05, are very similar. On daily basis, they act in the same way. So this right images show you the correlation between the two products for here on a daily basis, and correlation is very high. So there are no differences between the two products. This is again H05, so you see the behavior is very similar to the other products. What happens if we use satellite precipitation as input to the hydrological modeling instead of the ground data precipitation. In red one, you can see the discharge simulated by the model using satellite precipitation. Green, the model using ground data, so rain gauges data, and the blue line representing observed discharge. We measure the performances of the hydrological modeling using Nash Sutcliffe efficiency coefficient. So with ground data, the efficiency is good, 0.63. Efficiency equal 1 means that observation and models are exactly the same, so the model is perfect. Negative efficiency means poor results of the model. In this case, we have quite good results, quite good capability of the model in reproducing the observed discharge using ground data. If we use satellite data, so the efficiency is reduced, heavily reduced, and this is general behavior that we usually observe is if we directly use satellite precipitation as input. Not always true. In this year, June 2015, May 2016, if we use directly the precipitation, the efficiency increases. Okay, for this section, not for this other section. This is especially due to the fact that in this year, ground data overestimate probability. So the model with the ground data overestimate discharge. This is just a small summary for this test basin. The blue is the efficiency of the model using ground data, and the red one is the efficiency using satellite data. You can see usually the red efficiency is lower than blue. So this means that the direct use of the satellite precipitation data into the hydrological models reduce the performances of the model. Then we combine with the modified conditional merging algorithm of Levy that Prado presented. We combine rain gauges and the H03 product. In this picture, you can see some particular instance of precipitation. In this case, on the left, interpolated rain gauges on the basin, and in this case, the merging, so the combination between rain gauges and satellite data. As you can see, there is the structure of the rainfall field is modified. And if we compare at catchment scale the amount of rainfall, the mergings tend to reduce the amount of precipitation. And for this year, the simulation benefit of this behavior. So the efficiency using the merging is increased from 0.63 to 0.77. And as you can see, not for all the events, the use of merging leads to better results, but on the whole period, the performances using mergings are better. This is true also in this other here, but not always. So in this year, for this section of the catchment, the merging leads to the worsening of the performance of the model. So generally, the use of merging can lead to improvement in the capabilities of the model in reproducing discharge. Now we'll show you some other example of another basins. This one, another of our test basin in yellow is the average precipitation using the satellite. in blue, the precipitation are using only rain gauges, and in orange, the merging. So you can see also in this case the general behavior that I mentioned that is present also here. So there is an underestimation. This is true for all the seasons. So that's true summer, winter, and so on, and more or less for all the months that we see here. And the same behavior happens in this other basin. The correlation on three hourly basis are 0.38 and 0.35 for those two basins. Again, if we consider the correlation of a daily basis, the correlation coefficient improves, just a satellite. And again, also for this other two basins, Telemagra, if we force the model with the ground data, the blue, this case, or with the merging, the combination, we sometimes improve the behavior of the model. So in this case, we better reproduce the high values, and we slightly better reproduce the low value of the discharge, represented here as a duration curve and not in the magnograph. So to the conclusion, I reported here for all the hydrovalidation years and for the different catchments that we tested, the efficiency result. The red bar represents the performances of the model using merging, and the blue bar the performance using rain gauges. As you can see in this case, the mergings lead to an increase of the capabilities of the model and reproducing of certain discharge. It's true for this basin in this year, in this other year, for this other basin, and again here. Again, for this 2017 basin. It's not always true. For this case, the merging reduced the performances of the model, and again, the performances are reduced also for this year. So not the reduction is not big, but it's present. To try to have a general conclusion, we can say that usually the satellite precipitation product underestimates precipitation at catchment scale, and the direct use of this product in the hydrological model usually, it's not always true, but usually leads to a deterioration of the performance of the hydrological model in reproducing the discharge. While the use of merging, so the combination between rain gauge and satellite product, leads to a benefit in reproducing the discharge if consider annual statistics for 5 basins on 9 tested. And if the performances of the model are decreased due to the use of merging, this decrease is usually small for statistics. So this general conclusion. That's all from me. I thank you all. We have, let's say, another, I think, very quick part related to a small exercise that Andrea will show you.
Okay. Good afternoon, everybody. I'm Andrea Libertino, and I will briefly introduce you to the tool that we have prepared for providing you a simplified instrument to independently test the added value of merging HSAF satellite rainfall product with ground station data in the framework of the flood estimation. In the detail, we have developed a Jupyter notebook for easily compare the difference in the output of the MISC hydrological models developed by CNR IRPI by using respectively HSAF H0.5B precipitation product, rain gauge data interpolated with the GRISO algorithm, and the conditional merging of the two. To set up the Flood Lab environment, you can download all the material from our GitHub repository. You can find here the address. Then it is required to install the Conda Python 3 virtual environment using the setup provided in the related folder that is available both for Linux and Mac. Once the virtual environment is installed, you can activate it, go to the Flood Lab folder, and launch the Jupyter Notebook. A browser window will open, and then you just have to select the Flood Lab merging script to launch it. The basin case study that is implemented is the Tiber River Basin close at Monte Mario in the central part of Italy. The basin has an area of about 5,500 square kilometers, and the dense network of automatic rain gauge station is provided for the area by the local regional environmental agencies. The MISC hydrological model is a lumped model and requires input rainfall data averaged on the basin area. The data are provided in the Flood Lab folder in a text file called Tevere data.txt for the years 2018 and 2019 with an hourly time resolution. In the detail, the first column reports the reference date time. The column between 2 and 4 report the hourly cumulated rainfall average on the basin area, respectively derived from GRISO, from HSAF, and from the merging. The fifth column reports the hourly discharge of the Tiber River recorded at the Monte Molino gauging station, and the sixth column reports the average temperature over the basin required as input for the hydrological model. Another text file is included in the Flood Lab folder that reports the calibrated model parameters. The first step of the notebook involves the import and visualization of the data. The study period can be modified by editing the start date and the end date parameters. Feel free to test any period included in the input data, but be careful that long periods can require large computational time. In this step, the notebook also imports the set of model parameters that can be directly modified in the TXT file. Then the notebook gives you a first overview over the whole period, first comparison between the different rainfall products. On the top, there is a comparison between HSAF in blue and GRISO in green. As expected, in general, HSAF seems to underestimate the average rainfall amount. At the bottom, there is the comparison of the average rainfall between the merging in red and the rain gauges in green. Despite the similar behavior, locally, some slight difference seems to arise. To understand these differences, we have carried out an example on a shorter period. Let's see, for example, the map from the cumulated rainfall from the 15th to the 23rd of November. The underestimation of HSAF, that is the map in the middle, is clear, as you can see from the maximum value of the color bar. We have in general smaller cumulated rainfall, but the improvement due to the use of the conditional merging can arise. We can see in this figure the station, the rain gauge station that were active the day of the maximum rainfall amount in this period, the 17th and 18th of November. As you can see, the green dot, the gray dot, represent an area where a lot of rain gauges were not active. That correspond to the area, to an area of high rainfall according to HSAF. So by merging the rain gauge conditioned with the field of HSAF, we have here in this area a larger rainfall amount compared to the one that we have obtained by just interpolating the rain gauge without any condition. The second step is the model run. These are the command line that are used to launch it. In this example, we have used the same set of parameters for all the rainfall product. If you want to provide different parameters, you just have to uncomment this line and provide a proper parameter file. Considering the column in the original data file, we remember that the second column was HSAF. So for the side on which column to perform the model, we just have to set the column name to simple P. So here P is the second column. The second column is HSAF. And so the model will be performed on the HSAF series. As output, the notebook provides you a graphical representation of the output. The red line is the simulated discharge, and the green line is the observed. As expected, HSAF underestimates the discharge due to the underestimation of the rainfall, while the performance for GRISO and the conditional merging are quite similar and seem both quite good. As a last step, the notebook allows you to focus the comparison on a shorter period. For doing so, you just have to select an extract of the original period, setting this start zoom and end zoom window. The output figure will be saved in the flood-proof, in the flood lab folder with the name that you specify here. An image like this will be produced. This is for the period from the 15 to the 23 of November, the one that we have previously seen. The differences between the merging that is reported in black and the GRISO, that is the blue line, compared to the green area that is the observation, is clear. We remember that we have some problem over some area of underestimation, and this is reflected in the output of the model. The inclusion of the spatial conditioning field allow a better representation of the input rainfall that led to a better capability of the model to identify the peak value that, as you can see, is almost perfectly represented. So all the data are, as I previously mentioned, available on the GitHub repository. Feel free to test the products with different setup. You can change both the period and the parameter. And if you find any problem, feel free to write us an email, and we will try to deepen the problem. That's all from this part. And if you have any question in general, I think you can do. Thank you for your attention.